Hey, welcome back to Yeyu Lab. Do you still want to build a real-time assistant that can see, can hear, can talk back to you like our previous screen sharing assistants? That's our multimodal real-time projects, and we've been building these kind of projects for a long time, and you can approach this in a couple of ways, like using the Google AI service live API, which is so convenient but come with limitations like the session caps and experimental status and the token limitations. Or by going to the open source solution. The open source solution, like what we have introduced before, often involves combining several models because there's no such open source models that can independently work like Gemini Live API. You must have the Whisper model for hearing and Gemma 3 or Q1 model for understanding the image and text, and the Kokoro model for TTS, that is for the talking capability. This gives you amazing control and privacy because they can be deployed in your own server without much GPU resources. But it does mean managing several different models working together that creates the performance issues and complexity. Today, we're looking at a fascinating new player in this open source space, Microsoft's Phi-4 multimodal model. Which makes Phi-4 particularly interesting is its design as a single unified architecture that's capable of processing speech, vision, and text simultaneously and generates text output based on these multiple inputs. This just gave me an idea whether it can potentially replace the separate ASR model like Whisper and multimodal VLM like Gemma or Q1 components in our pipeline, which simplifies the architecture and potentially improving efficiency. Phi-4 multimodal is a 5.6B parameter model that boosts impressive performance, particularly in automatic speech recognition and speech translation, even outperforming the specialized model like Whisper v3 on some benchmarks, even outperforming specialized models like Whisper v3 on some benchmarks. While its factual QA capabilities might lag behind much larger models, its unified multimodal processing and efficiency make it very attractive and compelling choice for our real-time interaction scenarios. So in this video, we will explore how to use Phi-4 multimodal model and Kokoro TTS like before to build a real-time multimodal backend. We will cover the basic interaction with Phi-4 together with the designer of our backend server and how we implement features like streaming output and interrupt handling to make it a real practical application. Before integrating the Phi-4 into a full real-time server, let's get a real quick feel for how to load and interact with a model locally deployed using a simple Python script. This will help us to understand the core API and prompt formatting. So you can find the model in the Hugging Face, and it lists the technical reports and the cookbook to tell you how to use the Phi-4 to do the various multimodal tasks. So to run the model locally, you should have a GPU environment to provide minimum computing resources. So if you have a GPU with more than 12 GB VRAM, it should be okay for this project. But if you haven't, you can find an online GPU environment temporarily to run your service. So I choose run pod IO, which provides various options for different type of the GPU from NVIDIA to meet your requirements. So for this project, we can choose a very low cost GPU like the RTX 4000 only for 20 cents per hour. And don't forget to select the public IP, which will be benefit for our multimodal server development to expose our WebSocket to the internet with the public IP. And you can also select the secure cloud for higher price, but with more confirmed resource providing officially. So normally for the text purpose, I use the community cloud that is shared by the community, which provide very low cost. So in this project, I choose an RTX 4000 Ada SFF GPU environment for only $0.2 per hour, and which is quite enough for our application. So it will provide you the connect strings via SSH to help you to log into the system and deploy your code and models. Okay, so let's see the code. So in this test demo, we will only check how to feed the Phi-4 model with images, text, and audio input at the same time and see how it's performed by its output text content. And we will perform the output as a streaming style, how quick this small local models performs in efficiency performance. So let's first run the demo. In this demo, I will feed the model with a recorded wave audio, which is recorded by my voice to ask the model to do some task.
Which country do you think this picture is happening? Give me some evidence and resource.
So it's basically a prompt to ask the model to decide which country in this image. And what image is that we will provide a default image URL, which is a picture that shows a place with a Chinese traditional construction. And also in the system prompt, I also tell the model the instruction to perform the text with natural and oral language, and also tell the model to call the user by his name is Adam. Okay, so let's quickly run the model. Okay, the model and its checkpoint shards has been successfully downloaded and preloaded. You can see from the NVIDIA command, it consumes about 10 GB VRAM from the GPU memory, which is not quite big for its size of 5.6B model. So in this demo app, we don't have to load a different audio or images. We just type the fourth option to directly do the multimodal processing with audio and images together. Okay, let's just run 4. No need custom prompt because we already tell the model to follow the audio's instruction to perform the task. Okay, start. Hey Adam, this picture seems to take in China. The Chinese characters on the building and the style of the architecture suggests that this is likely a scene from a Chinese city or town. That's a quite accurate response. This picture is probably taken from somewhere of Chinatown. And also you notice that it tells, hey Adam, so whatever the system prompts, the text prompt, and audio and images are all fed and respected by this model. That's a great result that gives us confidence to move into a real production service by only adding a TTS model to convert this text to a real natural audio response. So from the code, you should follow the instruction to install all these packages in the requirements and make sure you type the right model path that from Hugging Face, Microsoft Phi-4 multimodal instruct model. And the first step is to load the necessary components like the processor, like the model, the generation configuration. Since the Phi-4 is a relatively new model, we often need to load it by set the trust remote code as true from Hugging Face. Don't forget to install the flash attention with the version 2.7.4.post1 as for the newest version to support flash attention 2 that is mandatory required by this model. And then here is the most important part of this code, that you need to take care of the structure of the prompt, because the prompt is a little bit complicated with the text, audio, and the images. So firstly, you should have the user prompt with the format of user, assistant prompt with the header of assistant, and the prompt suffix with the end. And here we have the system instruction defined to direct the model's response in high level. So for the real prompt format, you can go to the generate multimodal function, and in here we provide the system tag, the system end tag, the user tag, the user end tag, and the assistant tag. So for the entire prompt, it comes first with the system instruction comes first with a brace of the system tag, followed by the user's turn, start with the user tag, and with the audio 1 following the user tag, and insert a text prompt that's freely designed to direct the model to understand the relationship between the audio and the images. Like here, I ask the model to answer the question in the audio based on the images in detailed description. And following that, there's an image 1 tag indicate that here is the image of this prompt, and end with a user end tag. Then finally add assistant tag to let the model to follow up the assistant content after the generation. Then we put the text prompt that we designed here into the processor, and the audio input and the image input, which is basically a link to the internet or a local directory to the audios and images as a member of the lists, to ask the model to make a multimodal generation. To get a real-time output that we have experienced just now, we use the Hugging Face SDK API text iterator streamer, which allows us to iterate over the generated tokens as they becomes available from the model running the backend thread. This is the foundation for our real-time streaming experience. So you can find the complete text file script in my GitHub repository to experiment further with different inputs and prompts by yourself to have a more deeper understanding of the Phi-4 advantages. Okay, so now we are going to integrate Phi-4 multimodal and Kokoro into a full WebSocket backend server. And this server will handling the incoming audio from user's microphone and the image data that potentially can be the pictures that taken from user's camera or the screenshot images from the screen sharing widgets on the Google Chrome, and process these inputs using Phi-4 and synthesize the response audio using Kokoro and send it back to the client in real time, and our client can perform the audio playback. So let's check this demo first. Here I use the Vite framework to simply develop a front-end service, real-time multimodal assistant by local models, and provide a preview window from the screen sharing. And you can start screen sharing by press this button, and chat history that's coming from the backend with the transcript text from the user and assistant. Okay, so let's start. Hey, what do you see in this image?
The image shows a street scene with a red stop sign in the foreground, a black SUV parked on the side of the road, and a traditional Chinese gate with red and gold decorations in the background. There are also some white statues and a sign that says Optus.
So which place do you think this picture is happening?
The image appears to be taken in a Chinese-speaking region, possibly China or a Chinese community abroad. The presence of Chinese characters on the sign and the traditional Chinese architectural elements suggest that this location is likely a Chinese market or shopping area.
Can you find out the English words that shows in this image?
Stop.
Could you find out more English words, maybe 3 or 4 English words in this image?
The image contains the words stop and OPTUS.
What time do you think this image is happening?
The image does not contain any information about the time it is happening.
Now let's check the core workflow of this application, that including the Python server, which is the most important in this video, and the browser client. The client continuously receiving the images and audio PCM from the microphone and screen record input by the user, and continuously push this data into the server via WebSocket communication, so that in the server, the first stage is the audio speech detection module, which identifies the speech segments from the real speech or the noise or the silence, because the audio is continuously pushed to this speech detection module all the time. There's no VAD functionality on the client side to make the client real lightweight. And there is an image receiver that caches the latest image periodically received from the front-end client. So by the detection, the confirmed speech segment will be pushed to the Phi-4 multimodal module, which is the core for this Phi-4 inference. The Phi-4 processes the speech segment with the image together to potentially generate the text response based on the audio and image. But also, if the speech is not quite clear, it will reply to the speech detection, okay, this is still a noise, or there's no speech signal, and it will not interrupt the later workflow for the real generation. And after the generation, it will output the text trunk with several stages to make sure the streaming stages can be pushed into the Kokoro to let the Kokoro produce the audio much more earlier, before the end of the entire response, so that when the first initial text trunk pushed to the Kokoro, the remaining text stream will continuously push to the Kokoro based on the trade-off of the length of the text and the time for producing the audio. And there is also an interrupt procedure that cancels the current generation if the system detects, okay, currently a new audio coming and the existing generation is still ongoing. It will cancel all this generation, either the TTS or the internal multimodal generation. And also this task will send an interrupt message to the front end to let the front end be notified to stop this audio playback, to make the interruption more natural to human interaction. And meanwhile, the Kokoro TTS processor synthesizes the audio chunks from the collected text chunks and send back to the client via the WebSocket for the client playing back. A key design choice for achieving the quick responsiveness is the implementation of the streaming generation and parallel TTS processor. Instead of waiting for Phi-4 to generate the entire text response, we process its text output as a stream. As soon as the first meaningful chunk of text is available, we send it to the Kokoro TTS processor to start synchronizing the audio. While the Kokoro is working on that first chunk, the Phi-4 continuously generates the next part of the text, and then we collect subsequent text chunks and send them to Kokoro for synthesis in parallel with the ongoing text generation. So this allows the audio response to start playing on the client much sooner than if we waited for the full text, for sure. Now let's look at the core Python code. We'll focus on the key components and how they interact with each other. You can find the complete main Phi-4.py file in my GitHub repository. Let's see how the audio segment detection and interrupt handling. The audio segment detector class is responsible for this task. It is designed to identify speech segment and managing the interruption flow. Here we designed a cancel current task function is called when the new speech is detected by add audio method, which detects the new segment while TTS playing is true. Here the speech is active. It will cancel the async IO task responsible for Phi-4 generation and Kokoro TTS synthesis, which is the key for enabling the response to the new input immediately. And the other key feature of this audio detection process is to find out the possible speech input by simply measure the audio energy to give a brief idea whether the speech is started. We have further speech detection in the module of the Phi-4 multimodal processing. So in the Phi-4 multimodal processor, this class handles loading Phi-4 and managing the generation process. The Phi-4 multimodal processor is initiated once to load the model into the GPU and the other initialization of the inference of the model, which we have shown in text 5 demo. One thing here is that you can design your system instruction in a custom way to make the model output in a more friendly, helpful tone with conversational language that sounds fluent when spoken. And also you can add additional commands like detection of the incomplete audio input or very short speech. So the process audio function receives the raw audio segment and prepare it for generate streaming. The generate streaming function constructs the prompt, which we are familiar already, set up the text iterator streamer, and start the model generation in a thread by the streaming output. It then collects an initial text trunk for immediate TTS processing and check if the initial output indicates noise and returning a special signal if it does. Here. Why it can do that indicate a filter, because in the custom prompt we ask the model to decide if it's a noise or background sounds. If so, it will reply exactly with the noise detected or no speech wordings that will be filtered by this section to release the load of model inference. And also here we should also add the set image function that process the input image into a local object prepared for the multimodal generation, together with the audio input. And here, let's move to the Kokoro TTS processor. So I mentioned Kokoro many times, but if you're not familiar with Kokoro, Kokoro is a very lightweight model with only 82 million size to convert the text input into the audio output. And it supports multiple language and multiple voices. So here we still use the English, but you can also use other language code to enable other languages. And also you can find the voice selection in their Hugging Face page to switch to another type of voice. So the size and the speed of generation is so impressive. Almost no one in the module area, in the TTS area, can catch that with Kokoro. It's perfect for the real-time generation. So similar to our previous open source backend, we use the synthesize initial speech function with minimal split for the first chunk, synthesize remaining speech with more intelligent splitting for subsequent chunks, which is a balancing of responsiveness and audio quality. And we also has a guard function collect the remaining text, which is responsible for collect the text from the text streaming generation in manageable chunks. We're looking at the text chunks as they become available from the Phi-4 streamer and allows the main handle client loop to process these chunks and send them to the Kokoro TTS processor for parallel synthesis and streaming to the client. And now we are stopped at the handle client, which ties everything together, managing the WebSocket connection and coordinating the tasks, including the Phi-4 generation, the noise detection, the TTS generation, and also the communication with the front end by using the WebSocket connection that was set up by the main function on the customer port 9073, and also has a simple receive audio and image function inside to continuously receive the messages from the front end via WebSocket connection, and these messages including the audio data and the image data. And that is mostly the key modules in the backend service. So we also has the front end to interact with this backend service to get the capability of the powerful Phi-4 and Kokoro models. So we will not describe the detailed code of this front end because it's quite common and described in my previous video. So again, you can find the entire code base of the both backend and front end in my GitHub repository, which designed to be compatible with each other. So this open source approach simplifies the model pipeline compared to using more separate models for each task and demonstrates the potential of smaller, efficient multimodal models for interactive applications. So you can compare the performance of this solution to the Gemini Multimodal Live API and also try more open source options in the future to adjust the experience of such real-time applications. Have fun developing, and I'll keep tracking the latest updates of the real-time tools, APIs, LLMs, and open source solutions. Thanks for watching. I will see you in the next video.